Hey, my name is Victor Zaccardo, and this is my demonstration project for MAE 535. Ampere's law relates current through a conductor with the magnetic field established outside of that conductor. This can be derived into an expression that approximates magnetic field inside a solenoid, but outside of that solenoid, it predicts zero flux, which just isn't the case. Biot-Savart's law can be derived into an expression that relates current through a toroid with the magnetic field a distance away from that toroid. This can be integrated over the length of a solenoid to approximate the magnetic field a distance away from the solenoid. So knowing this, I decided to build an ammeter. If you put a permanent magnet on a shaft and you put it next to a solenoid, when you run a current through that solenoid, the permanent magnet is going to try and rotate and align with the magnetic field created by this solenoid. If you put a torque that increases with angle on the other side of the shaft, the position of that magnet is then going to be determined by the current through that solenoid. Knowing that, let's take a look at my project. Alright, so here's my ammeter. It is a permanent magnet mounted on a brass shaft with two solenoids, one on either side of the magnet. I've marked the poles here, and what this is going to try and do is these poles are going to try and align with each of these solenoids when current flows through these two posts here and up through the solenoids. To provide a restoring force, I have 3D printed a cam here on the back. The radius increases as angle increases, so the torque on the shaft increases. And you'll see it provides a restoring force there, so it brings it back to zero. I've also added a brass stud there to stop it and add a 0 point. Got my ammeter hooked up to my power supply here. There's 5 volts coming out of it. There is 3.5 ohms across these two terminals through the solenoids. I've then got my multimeter measuring current, and that's also in series. And then I'm going to ground it out in one of 3 ways. There's going to be 2 large resistors in parallel, one smaller one in series, or just directly to ground. So that should correspond to 0.4 amps, 0.66 amps, or 1.1 amp. And these two should match. So the 2 large resistors in parallel reads about 0.4 amps, and these two match. The smaller one in series reads 0.6 amps, about 0.66, 0.67 in that range. And then the larger one reads 1.1. And that one is very repeatable, since there's so much force involved there. So 0.4, 0.66, and 1.1. So you can see that my ammeter worked, but it lacked a little bit in repeatability and resolution. A coworker of mine had this old millivolt meter that he let me borrow and take apart. You can see this is the last calibration it was done here. It checks the resistances that are in series with the galvanometer, and it was last calibrated in 1953. So this thing was last calibrated before my parents were born. There's a couple things I want to note here on the outside. There's this mirror behind the needle, which I could initially figure out what it was for. It turns out that it is to eliminate parallax error. So when you look at this gauge, you align the reflection of the needle up with your eye, so you know you're getting 0 parallax error. So I'm sure a lot of the low-end gauges didn't have that, so this is a very high-end millivolt meter. There is a ranging button here which selects which resistor is in series with the galvanometer inside, and there's also this button. I'll explain what this does in a second. So I've taken apart the millivolt meter, which is essentially a galvanometer in series with a selectable resistance. There's some resistors back here. There's a couple of things I want to point out. There's permanent magnets in here, and there's iron all the way around the back to minimize or eliminate any air gap, maximize your flux through there. There's also an iron core inside that coil there. It's captured by that coil, and this ring connects to the core in there, and so there's no air gap in there either, really maximizing that flux. I pointed out that button that was right here. And what it does is it shorts out these two terminals, which, if you think about it, is a coil in a magnetic field. So if it rotates, there's changing flux through that coil. So what that was used for was when the cover was closed, it would push these two together, and according to Faraday's law, it would damp out any movement in this needle here. So if I were to move that needle and not touch it, it'll move back and forth pretty freely. If I move it up there and then hold this down, there's a force generated by the interaction of that coil and the magnetic field. So there you go, proves Faraday's law too. Thanks for watching.